Yes, once again, I have to make this video at home because there was a problem with the videographer. What I'm going to start with is just kind of predicting what an NMR would be like for a very simple compound to kind of get you back in the game. Okay, so let's consider this very simple molecule. And as I told you, a good thing to do if you have forgotten how to do this is to just take a molecule every day and predict what its NMR would be like. Now remember, the 4 things in NMR. Number 1, you get a peak for each different type of hydrogen, or a group of peaks, such as a split peak. You get different positions depending on the environment of the hydrogens. And that's one of the things we're going to explain today. And then hydrogens that have neighbors split each other, and you get these splitting patterns. And that tells you different things. All right, so we want to kind of go through that, starting with the structure. So here's a very simple structure. First, let's determine how many different types of hydrogens we have. So everyone would agree that this is a unique type of hydrogen because it's 2 bonds away from these 2 chlorines. These I would both call HB. Remember, the bond is rotating here, so on average these would see the same environment. And then I'm going to call these HC. Okay, why are they different? They're both 2 bonds from bromine. These are the farthest away from the electronegative atoms. So your first thing you would reviewing, the first thing is you should see 3 different peaks, or groups of peaks, split peaks. All right, so there should be an A peak, a B peak, and a C peak, or groups of peak. All right, now let's talk about the relative positions of these peaks in the spectrum. So could you predict which hydrogens would be at the highest position in the NMR? And remember, one of the things we talked about was proximity to electronegative atoms. So if you're looking at this molecule, this hydrogen is 2 bonds away from 2 chlorines, and these hydrogens are 2 bonds away from 1 bromine. Chlorine is more electronegative than bromine, and the effects here are cumulative. So this hydrogen would be at the highest position. So HA would probably, I'm just predicting a little bit here, would probably be at about 5, approximately 5 ppm. And remember, ppm are proportional to frequency. Okay, HC would be at the next position, and HC would be at about 3 or a little higher ppm. And again, you could look this up on a table. HB would probably be around, I would say, 1.8 to 2 parts per million. All right, and I'm basing this, but you wouldn't necessarily be able to come up with the numbers, but you should be able to come up with the order. Okay, what about the areas? Okay, the areas, remember, under the peaks are proportional to the number of hydrogens. So what we would expect about the areas under the peaks is that HA to HC to HB would be 1 to 2 to 2. So I'm going to write 1 to 2 to 2. All right, what about the splitting? HA has 2 neighbors. So what would you predict? You'd predict HA to look like a triplet. Which would look like that, okay? HC, which is coming up next, the HC population has 2 HB neighbors. So HC should also be a triplet, but it would be a bigger triplet. Okay, I'm going to draw this in spectral form in a minute. And then the HBs have an HA on one side and 2 HCs on the other side. This could be a quartet, or it could look like some sort of complex multiplet because they're not exactly the same. So right now I'll say quartet, but I'll put possibly, and we'll get into complex splitting next semester, possibly complex splitting. And again, this is because the 2 sides are not identical. All right, so what would the NMR look like, okay, for this molecule? So we're saying the NMR would have a small triplet. Then at around 3 parts per million, it would have a larger triplet that would have double the area of this triplet. And then a little bit lower, it would have some kind of a multiplet. I'll just draw a quartet for now. But it's not necessarily that simple. So this would be 1.8. This would be around 3-ish. And I'm guesstimating these positions. Okay? That's what the NMR would look like. And again, this would be 1 to 2 to 2. All right, I just went backwards. Now we're going to go forward. So let's do a problem going forward. And what I want to do is introduce to you what happens with alcohols in NMR. Okay, so alcohols. Then I'm going to get into some theory, as I promised. Okay, and this is just to get you warmed up again. So I'm going to show you a spectrum that I have up on the web. It's not the most beautiful spectrum. Okay. What you can see here is, I don't know why that's happening. What you can see here is a peak that's way, I don't know, I'm having an awful time with this mouse.
You have to scroll.
What?
Move down a little bit. Move your pointer down.
Right.
Now grab it and move it up.
It's not working. Well, anyway, I'm not going to use the pointer. But what you're seeing here is a peak that looks like about a singlet at 7. This is going to have an area of 5. I'm going to explain this in a minute. This has an area of 1, and this is a quartet. An area of 1, and that's a singlet. And then you see an area of 2 here. A doublet here that's going to have an area of 3. Okay, so I'm going to draw this up on my board and just kind of go through it. So the spectrum looks essentially like this. And I'm doing this to remind you of some things and introduce you to some new concepts. There's a quartet, a singlet, and then a doublet, okay? We're going to give you the areas on these. This is at about 4.5. This is at about 3.2 or so, and this is at about 1.3. And remember, there's always this peak at 0, and that's the tetramethylsilane. I explained that to you in class. NMR is registered in terms of parts per million, and parts per million are proportional to frequency. Okay, so if I were gonna give you the areas on this, this is 5. The area of this peak is 1. The area of this peak is 1, and the area of this peak is 3. And this compound is C 8. H10O. Okay? All right, so that's our spectrum. So let's get back in the groove here. Remember, we were calculating the unsaturation number, and this would be based on C8H, and you guys were really good at this as I recollect, 18O. The difference is 8, that should be an 8 there, divided by 2 equals 4. Okay? Now remember, at unsaturation of 4, your brain should kind of light up, and you should be thinking about aromatic rings. Okay, that's where you should be. There's evidence that we have an aromatic ring because there's a peak at 7. All right? So how am I going to solve this? I'm going to erase this, and we'll refer back to the one that's on the web periodically. But let's put our little chart up and start solving it. Remember our table that we made? Now, it would be nice to have an IR here, but we don't have an infrared spectrum. So this is delta. Remember, that's the peak position in ppm. Area, that's the integral sign, which means area. Splitting. And conclusion. Okay? This is kind of my standard table that I use. Now, remember, a lot of times when we're down in the low end of the spectrum, we don't really use the position as much. But remember, things that are above 5, like aromatics, you've got to jump on them right away. So my first important peak is at about 1.3, and if you could just look at that one more time. My first peak is here at about 1.3, and it's a doublet. Okay, then I have a singlet and a quartet and another singlet. We'll go back to that in a second. So at about 1.3, this would have a relative area of 3. The splitting is a doublet. So let's review what this means. What this means is you would interpret this. This is what is here. This is what is near, right? What is here are 3 identical hydrogens. This would be a CH3 group next to a doublet, okay, which means the doublet means the fact that there are two peaks means that you have one less hydrogen neighboring than the number in the doublet. So you subtract one from this, and you would say it has one neighbor. So this is very likely a CH3 group next to a CH. Now, if this is really the case, we'll be able to corroborate this down the line. Okay, now at about 2.2, and I want you to take a look at that again. At about 2.2, there's a peak. You can keep looking at it. At 2.2, there's a peak. Okay, am I right about that? No, I'm sorry, at 3.2, there's a peak, and I want you to really take a look at this. That has an area of 1, and it's a singlet. Now, what I want to point out here is this is very characteristic of an alcohol. Alcohols, OH groups, usually don't split, and I'll explain why in a minute. And they really can be in any position in the spectrum from 0.5 up to about almost 5 parts per million. They tend to look a little broader too. So in a typical NMR spectrum, an alcohol will be a broader singlet. But at this juncture, you wouldn't really know what this is. You'd say, well, maybe it's a CH with no neighbors. You know, is it isolated? That it could be that. Or is it an OH? This should enter into your mind. How do they show up in the spectrum? But I'm just saying in terms of its sort of topography there, that looks like an OH to me. The next peak is at about 4.5, and it has an area of 1, and it's a really tiny quartet, okay, which I drew on the board before. We can look at that again. It's a very tiny quartet. You can see the small outer peaks and the two inner peaks, and in a few minutes we'll explain why that's so. Okay, what does this mean? This means you are seeing one hydrogen, and it has 3 neighbors. Remember, subtract 1 from the splitting that you're seeing, and that will tell you the number of neighbors. So this is likely a CH next to a CH3, and that's just corroborating this idea. We said we saw a CH3 next to a CH. We should have a CH talking back to the CH3. So this is just like verifying that idea. Now the question is, what is that? Is it a CH or an OH? But let's keep going. At 7, we have the very definitive aromatic. And remember, we have an unsaturation of 4. So that goes along with that idea. So the area is 5. Now remember, when the area is 5, you don't really have to think about it because there are only 6 positions on a benzene ring. Now, of course, we're taking a bit of a guess that it is a benzene ring, but it's a pretty good guess. Benzene rings are the most ubiquitous aromatic ring. All right? So you don't even get into the splitting here. It has an area of 5, and if you're really thinking benzene, that means 5 of the positions are filled with hydrogens. Okay, and then 1 of the positions is filled with a substituent, and that substituent is built from these pieces. Now, if you go into the bookkeeping phase of the problem, we have 6 definite carbons right there, and we have 2 definite carbons here, and that's the 8 carbons, right? So we know we have a CH3 next to a CH, and that's repeated here. We know we have a benzene ring. That is 8 carbons. And that being the case, and the fact that we've already taken care of the unsaturation, all we've got left to fill in is an OH. That's it. In other words, if I make this a different CH, I have too many carbons. So it really has to be an OH. So if you were, after you do the bookkeeping, you can conclude it is an OH. If you were putting this together, the benzene ring only has 1 connection on it. The CH next to the CH3 is a terminal group. In other words, it's one of the ends of the molecule, but it has 2 connections on it. One of those connections will be to the benzene ring. The other one has to be where you place the OH. Now, what is weird about OHs? Alcohols. Alcohols hydrogen bond, okay? That's the reason for the variable position, and I'm not going to explain that just yet. We're going to kind of work our way into that. But it's also the reason you see the broad peaks in the IR. That's due to hydrogen bonding. But the other thing about alcohols is the hydrogen is slightly acidic. At least it's more acidic than most hydrogens that are on carbon. And because of that, it's in what's called chemical exchange. So the way we run the NMR and the solvents we run the NMR in, the hydrogen is kind of like being tossed on and off into the solvent all the time. And that being the case, it's kind of like a neighbor that isn't really home. It's kind of like a neighbor that's half home, half away. It's the neighbor that works all the time, okay? So, and you know those neighbors that are always out of town. You never get to know them. So this hydrogen is essentially not residing on that oxygen sufficiently to have the magnetic interaction with its neighbor here. Okay? Now, if you get rid of that chemical exchange, which you can do, if you get rid of the chemical exchange, and you usually do that by neutralizing the solvent, if you get rid of it, this actually will split. But in the typical NMR, a typical proton NMR, these are things you have to learn as you go along. OHs have a variable position from 0.5 to like 5 ppm. It's a little different on different tables. In the gas phase, it's like at 0.5 parts per million. And it's usually a singlet. And that's actually kind of nice because you can usually pick them out. And it simplifies the splitting a little bit. But as I said, there are chemical means by which you can get that coupling back in there. Okay, so now we're going to do a little theory if I can get my mouse working here. So let's see if I can get going here. Oh, not good. Okay, let's see if I can get this thing working. Well, the right side of this isn't working. Can I have the mouse? I don't know how I'm going to use it here. Oh. Yeah, but it's not going to work on the screen. Okay, we're having a little technical difficulty here. I can't do it on the screen. All right. Okay, stop the movie and we'll continue it.